research in radiochemistry and its impact on the environment, particularly he studies radon gas. He's extremely active in promoting use of chemical demonstrations and all levels of education. He lectures all over the country, presenting demonstrations to students of all levels from elementary school to university. And currently he's a television demonstrator for the PBS syndicated series The World of Chemistry. Dr. Lang is also a professor of chemistry at the University of Wisconsin at Stevens Point. He is extremely active where he does research in electron spin resonance spectroscopy. He's extremely active in the American Chemical Society, which is the largest association of scientists in the world. After holding several local and regional offices, right now he's a member of the National Board of Directors and is a nominee for president of the American Chemical Society. So the elections are coming up later this year, and we wish him the best of that. He's long been interested in presenting science to the public, and he travels all around the country showing chemical demonstrations to students of all levels, again from elementary school to the university level, and to public organizations as well. Today they'll be assisted by Michael Morgan, who is a teacher. Michael Morgan. He's a teacher of chemistry at Narbonne High School. He is involved with the Institute of Chemical Education at the University of Wisconsin in Madison, and she also lectures at local universities, giving lectures and workshops, teaching new teachers to present science more effectively. He's also brought members of the Bravo Chemistry Club. So without further ado, please welcome Dr. Showalter and Dr. Lang.
Thank you. Glad to be here. Your countryside looks much different than ours. We still have about 6 inches of snow on the ground. You guys don't see that very often, huh? We left though, we're having a warm spell. You guys are having some kind of crazy weather, I know. We have too. We've been actually already had 50 degrees as a high. So that's unusual for us. Usually in January and February, sometimes we get as much as 30 below zero. We haven't had that this year. It's been nice. It's nice to come out and not have to worry about wearing big coats and everything. Pretty glad to be here. Have some nice people. We came today to tell you about some chemical demonstrations. The reason that we do this is to try to get people excited about science. We really feel that there's a real tremendous need to keep people interested in science. Not necessarily that everybody has to become scientists, although that would be great. But we want people to have a good appreciation of science. Many times what we read in the papers and see across the TV are only the bad things that concern. Many times Marvin will mention sometimes that the word, and so you hear the expression toxic chemical. That's really 2 words. When you say chemical, it doesn't necessarily mean that it's toxic, it's toxic. So we're trying to present chemistry in a better light.
Last year in our hometown of Stevens Point, Wisconsin, which you may have never even heard of Stevens Point. Not a one.
I'm not surprised.
It's right in the middle of the state. Right in the middle of the state of Wisconsin, and across our main streets. Last year when the high school was graduating and they were going to have some parties, they said, let's have a chemical-free graduation. What nonsense. How can you have a chemical-free graduation? How can you have anything that's chemical-free? I think what they meant to say is, let's keep our graduation, our high school graduation, free of mind-altering drugs, such as alcohol or some of the other things that are going around. They didn't want a chemical-free graduation. Our whole bodies are chemistry, aren't they? Everything around us is chemistry. You heard it mentioned that I'm a candidate for president of the board of directors of the American Chemical Society, all 150,000 members. They're willing to give you $1 bazillion if you can put a little sticker on anything that's not related to chemistry, or it's not the product of chemistry. Because everything around you is chemical and chemical in nature. And that's what we would like to show you some of those things today. We have a number of chemical demonstrations that we think are here, first of all, to be visually effective, and second of all, hopefully, will spark some curiosity on your part. And thirdly, since we're teachers, we can't get out of that teaching mode. We want you to explain it, or at least understand it from a fundamental level rather than being entertained by it. What are the reasons behind the way some of these things happen? Where should we start?
Well, there's a demonstration.
Well, that's opposite.
We okay? We must just tell you that we've come a long way. We did not bring our own equipment. All an area that we can drive. We have a van. We have a van full of equipment that we have. Michael was able to provide all of this equipment himself. So if we look a little bit uncomfortable or tenuous about some of the things, it's because we're not really sure about the equipment. Not necessarily that it's anything different. It's different, but not necessarily that it's anything bad, any worse or anything. So bear with us if we pick up the wrong flask or something like that. This one is a very old demonstration. You know that the two key words nowadays, if you go into, especially the elementary school with the kids, if you ask the kids, what's your favorite subject, do you think many of them will say science? No. And why do they say, if you say, all right, why don't you like science? Why are they going to say it? It's boring. And it's exactly what they say. Now, do you think that should be that way? And the two words now that are really the basis of trying to make it not boring are hands-on. Have you heard that expression? Let's do things hands-on. Let's just don't sit there and listen to it. Let's do it hands-on. I wish that I could get every one of you guys doing some experiments. Wish I could break you up into groups. We'd all do hands-on. Would you rather do that? It'd be more fun, wouldn't it? Why can we do that? You got enough? Break it up? Find groups? Sure. Go for it. We can't today. This one is a real old one. Listen to how Marvin tells the story that goes along with the chemistry.
At some time in the distant past, lived a man by the name of Ira Remsen. Unusual name, Ira. I don't see that name too often anymore. But Ira Remsen was perhaps, as far as chemistry is concerned, chemical education in the United States, he's probably the grandfather of very, very many people. He was at Foster at Johns Hopkins University back in the late 1800s, early 1900s. In fact, he's the one who discovered saccharin and how to prepare saccharin. However, he did not start out to want to be a chemist. He wanted to be a physician. And he says that he was sitting in a physician's office one day as a youngster, and he had to do the same thing as you and I have to do. If you ever go into a doctor's office, what do? You wait. And they didn't have Reader's Digest in those days. They had little pamphlets, and he was looking at a pamphlet that was entitled Chemistry, and he started thumbing through it and started reading, and he said, you know, I read the same kind of phrase over and over again, and he said it was nonsense, because he didn't know what it meant. The phrase that stuck in his mind and that he wrote about many years later was the following little phrase: nitric acid acts upon copper. 5 words. Nitric acid acts upon copper. Can you say that with me? Nitric acid acts upon copper. You know, he said, I don't know what that means. Oh, I looked around the doctor's office, and sure enough, there in one of the little old white cabinets, he saw a bottle. The bottle had a liquid in it, kind of sloshed around, and sure enough, on the bottle it said, I hope this is right.
I was wondering if he's ever realized this.
It's concentrated nitric acid. It was a colorless liquid. He says, you know, I think I know what nitric acid now is. It must be a liquid. Maybe it's a water solution of something. And sure enough, he dug into his pocket and he pulled out a couple of coppers, as he called them in those days. The big old-fashioned pennies. They're about the size of the modern-day quarter. He says, you know, I know what copper is. It's not like silver. It has kind of a red color to it. It's not like gold, which has a yellow color to it. It's not like aluminum, which is kind of without color. It's like silver. I know what copper is. What I don't know are the meanings of the words of the two that I haven't said yet. What are those 2 other words? Acts. I don't know what acts upon means. It's an old-fashioned term. So what he did is he put the coppers and pennies down on the tabletop and poured the nitric acid on it. I'd like to do that with you today, except we're going to do it in the following way. Notice the technique. You don't put the stopper on the table. And we're going to put a little bit of this nitric acid into this fancy flask, this round bottom flask. Okay? See the nitric acid pouring down in there. What color is it? Well, it's clear, yes. But does it have a color? So the way in which we denote that is we say that it is colorless. Okay? And I think you can see what we're going to do here. I'm going to put this little stopper in here. Okay? And I'm going to put that into like that. What I wish to do is to put the pennies in there. And they fall in. And you know, it's the same thing Ira Remsen noticed. There was a color change. There was an absolute color change. I'm going to go wash my hands off here with a little water if I can find it. How about that? I think I'm right in there. A little water.
That wasn't water, Marvin.
I want to wash my hands off a little bit.
What do you have? Marvin, Michael's got the story right here.
While reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I was determined to see what this meant. Copper was more or less familiar to me, for copper cents were then in use. I had seen a bottle marked nitric acid on a table in the doctor's office where I was then doing time. I did not know its peculiarities, but the spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words acts upon meant. The statement, nitric acid acts upon copper, would be something more than mere words. All was still. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A green-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored dark, suffocating. A gray-colored cloud arose. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out of the window. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers.
Marvin found that out, didn't he?
The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. Taking everything into consideration, this was the most impressive, expensive, and relatively probably the most costly experiment I had ever performed. It was a revelation to me. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn about it was to see its results, to experiment, and to work in a laboratory.
We have learned a third fact today, haven't we? Remember this brown obnoxious gas that was being piped over through this rubber tubing into this vessel. This vessel had some pink liquid in it, didn't it? As the brown gas was bubbling through the pink liquid, I think perhaps you saw a little bit of it escaping outside the saran wrap. However, it's still continuing to bubble up. But what happened to the color? The brown gas acted on the water, didn't it? Now this is continuing to react. I still see bubbles. Do you see bubbles coming out of there? That kind of thing. There is a fourth or fifth fact, and that is that this flask is very warm. So when nitric acid acts upon, or today we would say reacts with, when it reacts with copper, it generates heat. Now we in chemistry have a word for that, and talks about reactions that generate heat. Anyone know what that word is?
I bet they know. What's a word that we use in chemistry that means to give off energy? Yeah, exothermic, isn't it? Exothermic, meaning heat, out, exit, prefix, thermic, exothermic.
What if this had gotten cold? What kind of a reaction would that be?
Endothermic, good.
Goes in. Well, this reaction's not over yet. It ain't over until it's over. I think that's been popularized by some big brown bear or something.
No, baseball player.
Isn't it the brown bear?
No, it's the old Yankee catcher, isn't it? Yogi
He said-
Berra, not Yogi Bear.
Oh, Yogi Berra.
Yogi Berra.
What is Yogi Berra's famous saying? It ain't over until it's over. This ain't over yet, folks. This ain't over yet. Why don't we kind of keep an eye on that? It seems to have settled down. I don't see any more bubbling.
It's bubbling.
Is it bubbling? It's a bubbling.
Do you have any idea what might happen? Anything? Anybody have any ideas? Is this, pardon me? Change color again?
This one here?
That one change color? Or the other one, possibly? The hints that we have are, that one flask with the brown gas in it is warm. Now what's going to happen once it stops reacting? It's going to no longer giving off heat. So what's it going to do? It's going to cool down. Which takes up more space, hot gas or cold gas? Sure. All right, so what's going to happen is that flask cools. It's going to create a partial vacuum. Now you know what's going to happen? Okay.
There's water over here.
You think so?
And how's it going to get over there?
Through that tube?
Okay. And so, this is warm, but is it not terribly warm? If you've had a chemistry class, the temperature inside this flask right now is probably, let me check, significant figure, 62.685 degrees Celsius.
Oh, it's not. No, really.
Sensitive fingers. So if this is warmer than room temperature. Let's say that went up to 60 degrees. What's room temperature? About 20 degrees, isn't it? Hey, Okay, I'm talking, centigrade or Celsius. So it's about a 40-degree change, but when you're talking about gases, you have to talk on the absolute temperature scale. And so at 20 degrees is about 290 something, 293. And so it's going up to somewhere in the 330s. That's not much of a change, not much of a ratio.
You study gas laws? Remember those gas laws? I went to a high school one time and the teacher told me the way they remember the formula, that PV over T is equal to a constant. That kind of thing. Peas and vegetables on the table. Peas and vegetables on the table. You get it?
They're not giggling very much. All right, I'm not sure where
gas laws in. As the temperature goes down, pressure goes down, huh? They're directly proportional. Well, is it going to do it right now, Marvin?
Nope.
All right, so let's let Michael do one more. Now, if that happens, you got to keep one eye on that temperature. Huh?
Well, I'm unsure. See, this bottle arrived at our school last week, and it had a return address of the Persian Gulf. Nobody's name, it was just a bottle. They attached a note to it saying that they felt sorry about what had happened last year, and they were going to send us a genie to grant us 3 wishes.
Do you believe this?
In other words, you're trying to tell me this is a
Hamper him.
It's a magic trick. It's a magic bottle.
What's it covered with?
What's it covered with?
Let's ask them. What's it covered with? What kind of foil?
Aluminum foil.
You can tell, but I heard a couple way in the back there from some of those people that are older than the students. What they call this stuff?
Tin foil.
They haven't made tin foil in this country and sold it in the marketplace since 1945. How come we still call it tin foil?
Because our grandparents were.
There you go.
Tradition.
All right. So what are we going to do? What are we supposed to do with this thing?
I say we ask for 3 wishes.
Oh! You ready to get the genie out of the bottle? How do you do it? Can you rub it, Michael? What's the magic word? Abracadabra.
No, it's
chemistry. Take the top off.
Oh, okay.
Oh.
Chemistry. Uh-oh. Oh, genie.
That's a violent genie.
Great. Holy smokes, what's happening in the flask?
What? Look at the flask. All kinds of things happen at one time.
Now do you understand the meaning of the words acts upon? Chemistry is an action.
Marvin, I know what did it. The genie did it.
The genie did it, huh?
Hey, Don, where are my pennies?
They're in that.
They're in here?
You put them in that flask right there.
This one here?
Yeah. You put them in there. Shake it up.
What happened to the pennies?
Don, those are my last 2 pennies. We got 4 more shows to do this weekend.
Michael, I'm sorry. Where'd my pennies go? Where'd Michael's pennies go? They reacted with the nitric acid. I heard, did anybody say they dissolved? Did you say that? All right, hold on a second now. If you take sugar or salt, put it in water, evaporate the water off, what do I get back? Sugar and salt. If I evaporate this water off, which is really just the blue water there, if I evaporate that off, do I get 2 pennies back? Do I get copper back? Nope, I won't get it. You know what I'll get? A blue-green powder. You know what that is?
It's like how do you do?
Copper nitrate, yes. It's copper nitrate that comes back out of there because we actually had a chemical reaction occur. And so the metal went into the ion state, didn't it? It went as an ion, went from copper metal into a copper ionic state. So it will not come back as the metal if we evaporate the water off. And you notice there's the brown gas still left in there? You notice when it came off of there, it really came off with a lot of force. The water came over there. What was happening is that brown gas was actually reacting with the water. I shouldn't say it dissolved again. You do balancing redox equation?
Not yet.
Not yet. If you get into that, let us give you this one, please, Patrick, and have them when they come to here balance. It's a nice balanced equation. Disproportionation. Good equation to balance that you'll come up with. Maybe it'll remind them about this reaction itself. But there's an oxidation-reduction reaction of that NO2 gas that goes in there that forms nitric acid and NO gas. And the NO gas is colorless.
Boy, that stuff's hot. It's genie.
What kind of reaction is that? Exothermic.
What was the stuff that came out of there?
All
I
right.
mean, the gas, the thing.
It did not come from Desert Storm or whatever you say it was.
That was the return address.
It came right. I made that up. You know what I put inside there? Hydrogen peroxide. You know the formula for water? They say, oh, what's the formula for hydrogen peroxide? H2O2, beautiful.
What's
What's the
H2O4?
difference? One more oxygen. Would you drink water? Sure. Would you drink hydrogen peroxide? No. Well, they're similar. Why wouldn't you drink it? It's a very strong, as we have it in here, oxidizing agent, isn't it? It would hurt you. But gosh, it's so similar to water. What would it like to do? What would hydrogen peroxide like to do? It'd like to turn into water, wouldn't it? What could we add to it to make it do that? A catalyst. A catalyst to do that.
In fact, the hydrogen peroxide that we buy in the water solutions that you perhaps have at home in a refrigerator for wounds and so forth, what happens when you put that hydrogen peroxide in a wound? It kind of bubbles and drops and foams, doesn't it? It's releasing what?
Oxygen, sure.
So if we were to put something like blood or the heme portion in hemoglobin, the iron ion or other transition metal ions will cause the decomposition of hydrogen peroxide. And here's what Don put in there. Ooh, icky old bag.
Tea bag.
That little tea bag. And he put a catalyst in there. This catalyst, it turns out, was
Potassium iodide.
potassium iodide, something that caused the decomposition, just like the wound. Except here it happened very rapidly. And you didn't put in hydrogen peroxide in the refrigerator.
Nope. I put in, if you would go to the drugstore and buy hydrogen peroxide, you know the percentage? You know, we always worry not only about the material itself, but also the concentration of it, don't we? That certainly matters. Remember what the concentration of hydrogen peroxide is in the store? 3%, isn't it? 3%. And we can put that, and actually, have you ever had to put it in your mouth? And just get a sore in your mouth sometimes? Ooh, awful, didn't taste it stuff. You're not supposed to drink it. You're supposed to be able to rinse it out like that. Well, you can go to the beauty shop if you wanted to and kind of tint your hair. You ever heard of that? 12% they use there. They say 12 volume, which is something close to 12%. This is 30%. If you put this on your hair, it'd bleach your hair right before it all fell out. It's really strong stuff. 30% hydrogen peroxide. The catalyst causes it to decompose into water and oxygen. All right? Knowing that, it wasn't a genie that came out of that bottle. What did you see come out of that bottle? Well, can't see oxygen. Can you see oxygen? It's in here. It's in this air. We can't see it. You know. Well, you can't see water vapor either. You can't see steam. Are you argue with me with that? Because steam is what? What do you say? We have ice, liquid water, and steam, right? Steam you can't see. It's invisible. But what happens is that steam is water over 100 degrees Celsius, over its boiling point, right? What happened when that 100-degree steam came out and hit this cool atmosphere? It condensed. All right, give me 3 words of what this is now. You had 2 of them before, but put that 3rd word on there. Condensed water vapor. It's condensed water vapor. And I wish I could take you all back to Wisconsin and show you. We should bring a picture, a big picture, a slide or something, or one of that. But you can't see it, and you missed it. Back in Wisconsin, if you think of Wisconsin other than cheese, they call it the cheese heads, you know. Other than cheese, you know what we're well known for? Making paper. We have lots of paper mills. And one of the things they use tremendously in the paper mill, or in the processing, is steam. And so as you go by a paper mill at 20 below zero outside, you see this big plume coming out of that stack. What is that? Condensed water vapor. But if you look right near the exit of the stack, you'll see a portion that's invisible. What is that? That's steam. That's steam. It has yet cooled enough to condense because of the hot gas coming out of it. We were riding recently to do a program nearby us at night. The sun was just setting, and that light, the sun was going through that condensed water vapor, the cloud, and you could see that invisible part. It was perfect. I should have taken a big slide and shown you a picture of it. But condensed water vapor, not steam. I've been talking too much, I don't know.
No, it's about this one.
Okay.
They like colors.
You like colors? What's your favorite color? Don't tell me yet because of trouble. Mary, will you help us? We need to decide, when I ask these nice people what their favorite color is, we need to decide, Patrick, we can decide the general favorite color. All right? We'll count to 3. Say your favorite color one time for me, if you would. And let's see if we can decide what the majority favorite color is. 1, 2, 3. Green.
Come on!
Green. 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 Okay. And we're making it turn green when we tell it to turn green. Well, not yet. We've got to do it in time intervals. So we want to show you the chemistry is predictable and ordered. So what we want to do, we want to add 2 solutions. Mark has one behind here. How would you describe that one?
Kind of colorless with a little bit of white bottom.
A little cloudy, if you would.
Start
out. Colorless, clear in the front here, huh? Those are the pairs. We want to mix 2 pairs, or the pairs, 5-second intervals. How do you count seconds regularly? We never say 1/1000. One what?
Chemistry.
Chemistry. 1 chemistry, 2 chemistry. We're going to try to be real regular.
The universally accepted way to count seconds.
We're going to go up to 5. Once we get to 5, start over again. And so every time we say 1, Marv's going to pour in here. So we have these set in 5-second intervals. All right. Then once we get them all in, watch this. When it turns green, start counting again. Every time you say 5, the next one will turn. You believe that? Well, what are we going to do?
We wouldn't be here if it wouldn't work.
Let's try it.
All right,
Here we go.
1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry.
All right, got him in. All right, wait a minute. Wait a minute. That first one turns green.
All right.
Michael,
1 chemistry, 2 chemistry, 3 chemistry,
whoa!
1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, now! 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry!
What the heck happened?
Is it green? Wait a minute, by definition, it's green. It's your favorite color. Don't you tell me different.
Now, when we do this, it's not going to come down to whatever favorite color.
It sure is.
It must have been Michael must have made that up wrong, you think?
Blame it on Michael.
I can fix it. I can fix it. Now, I know that Narbonne's colors are green and gold. Okay? And I know that Dr. Lang is very fond of this color that he has here, this very deep blue iodine color. So I want to satisfy all of you at the same time. I have a green solution here. And down here I have 3 beakers. When people travel a lot and do lecture demonstrations regularly, they get to be known for specific reactions. I know that Dr. Lang is very well known for his physical chemistry demonstrations. Dr. Showalter spends a lot of time talking about radiochemistry and radon specifically in your household. I, since my sophomore year in college, have been known for liquid nitrogen demonstrations that I do that are rather innovative. But my favorite demonstrator of the past was a man at Princeton named Hugh Allier. And what a lot of people don't know about the campus at Princeton is there's a building there called Nassau Hall. Now, for a very short time, several hundred years ago, Nassau Hall was the capital of this country before we had settled the capital in Washington. And Nassau Hall is a brilliant gold and black color. Okay? Hugh Allier, famous chemical educator at Princeton, came up with this reaction and has done it worldwide. And he likes to sing the Princeton fight song while he does this demonstration.
Go, Michael.
You going to do that, Michael?
I don't think I'm going to subject you to having to listen to me sing. But I want to satisfy everybody's color choices. So I'm going to put a stir bar in here. And we're going to look down here and see that we have a green solution. Solution A goes into solution B. B goes into C. We stir, and we try to think, can we get a gold solution? And then can we satisfy our friends from Wisconsin?
Hey!
To get a black solution. This is called the old Nassau clock for Nassau Hall in Princeton. It's just another simple variation on the iodine clock reaction.
So we take it, Michael. We had the green one, which was really blue. We've had the orange one that goes black. We like to call this one the witchy pumpkin. Not the cat eats the pumpkin. I mean, around Thanksgiving or Halloween time, don't you have pumpkin? So this is a good demonstration to do in a class, probably on the 31st of October. But you have orange pumpkins and you have black witches that eat the orange pumpkins. Don't tell me a black cat. I haven't seen cats eat pumpkin trees yet. I haven't even seen a witch eat a pumpkin.
No. That series of 5 that we did is a traditional reaction, also called the iodine clock reaction. It will only turn a real dark, deep blue black. So usually when we ask crowd, and look around you and probably on your clothes what the most common color is, what would you think the most common color would be? Blue or black? Yeah, most people will say their favorite color is blue for some reason. You guys said green. We can only make it turn blue. That second one, there is an iodide precipitate that is orange that we form, and then the last part where the black came in, the black, that's the same iodine clock reaction as on the whole.
Well, Michael mentioned the Persian Gulf. We started doing this demonstration several years ago, but the one we're about to do now really seemed to have come into its own in the last year or so. Perhaps it's the additional patriotism. Perhaps it's the idea that we had people fighting over in the Middle East. But this particular one's called patriotic colors. What do you think those 3 colors are?
Red, white, blue.
Now, we don't have a flag here. But, we're about half done. Perhaps you could stand up. Perhaps you could just sing the national anthem all together.
Want to do that?
Sure. Yeah, there we go. Come on, stand up.
How about we sit and hum?
We're going to sit and hum. All right, we're going to sit and hum.
All right.
Let's mix this one together.
Here we go.
Hold the hand here.
But it won't turn color unless you...
Sit and hum. Here we go. They're not very cooperative today, Mike.
Keep humming, it's not working.
You got it louder, it won't happen.
It's red glare, the birthday in air. Hey! Through the night that our flag was still there. Oh, say does that star-spangled banner yet wave for the land of the sea free and of the brave. That's about it, guys. Come on in there.
That was a little weak, isn't it? What color is this? That's close enough, isn't it? Some people say it's pink. That's red. That's phenolphthalein. You use that in your titrations at all? Have you done titrations?
Very common used indicator.
Also, it's an X-lax. If you need a supply of phenolphthalein, you can always go to X-lax to get that out of there.
What's that one?
This one is a relative. This is what I say this was? Phenolphthalein. This is a relative. Thymophthalene.
You have to say that with a lip.
At the little lip.
Okay.
Thymophthalene. This one is supposed to be a white precipitate. Maybe I didn't add enough.
That's possible.
This is magnesium chloride originally in there. This reaction produces hydroxide ion. Okay? And so the hydroxide ion indicator of base. This was the phenolphthalein colorless and acid, pink and base. So it turns, as soon as the predominant hydroxide ion concentration turns pink. This one turns purple. It's colorless in the acid solution. And this one's supposed to precipitate magnesium hydroxide. There's a little light today, isn't it?
But where can I get magnesium hydroxide?
Oh, we're getting magnesium hydroxide. Go to the drugstore. We get an upset stomach. Why do you get upset stomachs? You eat too much, and your stomach is overworking. It's producing more acid because your stomach is very acid to help in the digestive process. Too acid, what do you got to add to your system to neutralize that? A base. What do you add? Magnesium hydroxide. Only they don't call it magnesium hydroxide in the store. They call it MOM. Milk of magnesia, sure. So if you have a little problem today, we got a few things up here that we can help you get a little regular.
Let me just put this one out here and have you take a look at it. Again, 3 solutions, colorless solutions, formed together. Isn't that amazing?
What color is it? It's yellow. That's beautiful, Marvin.
Are you sure?
Wait a minute. Wait a minute. What color is it now?
It's kind of faded right in.
It's blue. That's great. Is that what it's going to do? Whoa! What color is it? Wait a minute. You said it was blue. It is blue. I thought you said it was yellow. It will be, huh?
these reactions. Notice it goes through it fades out of the blue. I see it on, those of you who are from front, you can see that there's some bubbles being generated, a little bit of gas. It goes colorless for just a moment, then it's an amber color, and then it turns a dark blue color. And it keeps going back and forth like that. It's called an oscillator reaction. And if we could understand the factors that influence an oscillator reaction, perhaps we could make some application to physiological chemistry. Stop and think, aren't many of your own body functions on some sort of an oscillatory fashion? Some things, like for example sleep, you do that on a 24-hour basis. There's a certain number of hours each day. You get hungry. There are cycles that are not only on a daily basis, but on a weekly basis, a monthly basis, an annual basis. What kicks off the aging process? Which is some sort of a irreversible cycle, isn't it? It would be awfully nice if we could begin to understand those kinds of physiological reactions, and perhaps one way to model them is through a simple peroxide iodate oscillator, which this is. We know that one of the things that triggers this is just ever so much a small amount of manganese ion. There's manganese sulfate in here, and some malonic acid, and a few other things. But we really don't understand this reaction very well. One of the things that we had a seminar at our school recently, someone had put electrodes in here and watched the EMF, that is the voltage. How does the voltage change with time, especially as it's going through these color changes? And the voltage in the solution is changing wildly. And it seems to be cyclic, cyclic. So it's an interesting reaction. This will continue on. If you've been watching it carefully, I think you'll find that the time required for the first appearance of the blue color is getting shorter and shorter. In other words, the period of the reaction is getting smaller and smaller, and eventually this will all stay purple.
Okay, we only got 20 minutes left. Is that all we got?
I guess that's right. We're having fun.
Sorry, I'm going to show you all our things.
We talk too much.
Let's change this.
Okay.
What's that?
Glass bottle.
Big bottle. You know what this is? I like to call it a thermos bottle, but Marvin says I'm advertising for King Celia. That's a bottle like what you take your milk in. You bring your milk in with you in little Batman.
I have Spider-Man in mine.
Scooby-Doo? All right, what are we going to put in there? Something very cold? Something out of the air? Liquid nitrogen, yeah. What's this coming right here?
What's it doing?
It is. It's producing water vapor. It's going down because of the nitrogen with it. And it's also very cold. What's happening inside there now? What's it doing in there? It's boiling. Wait a minute, I told you it was cold. Is it boiling cold?
That means it must be freezing hot.
Is that true? It is true, isn't it? Because what we think about as boiling and freezing is based on water. But everything, every pure substance has a boiling and a freezing point.
It's boiling so rapidly now. Is it going to continue to boil? Uh-oh. It's starting to quiet down, isn't it? In other words, the inside surface here was so hot compared to the liquid nitrogen, it was as if we had taken a red-hot piece of metal and put it into cold water. Eventually, of course, the inside surface takes on the same temperature as the stuff inside. Remember, there's two glass surfaces here with the air pulled out. Now, last night, on the plane, I had some boiled potatoes. You know, they boil up the potatoes. Cook them that way. Isn't that what we're doing here? Aren't we cooking a racquetball? We're bringing the racquetball to the boiling temperature of liquid nitrogen. Are you cooking my lunch? You.
For the sake of science.
All right. All right.
What's going to happen to the racquetball? Wait a minute. What's freezing? Going from a liquid to a solid. Is that ball liquid when I had it out here? No, it was solid. What's it going to happen to the ball? It's going to get cold. It's going to get hard, isn't it? It's going to contract, isn't it? You think of the polymer chains in there getting closer together. It's going to become much more rigid. What's going to happen to the banana? Now, you could possibly say it's going to freeze somewhat because there's a lot of water in the banana, isn't it? But it's also going to become very hard. How hard will it be? As hard as a hammer? Yeah. Could I drive a nail on a board with a hammer?
Have you ever seen that?
A banana hammer? Let's try it.
Later we'll go banana daiquiri.
Well, this is not a banana daiquiri. This is since you're using it as a hammer, is called banana tackery.
All right, get comfortable, Scott.
Oh, Lord, I love the banana! I love it. Oh, the whole cotton mixed banana.
Grab that puppy.
Oh,
All right.
the banana just about died in there. Did we get balls cold enough?
Think we've cooked it up enough? Is it done yet? How do you check to see if the potatoes are done? You stack, yeah, that's right. You stick it with a fork, right? You know how we know if the racquetball's done? We throw it against the wall.
Yep. How's your wall here, Patrick? Concrete? Good, solid wall, huh? I'll put it up there so you can see it. Here we go.
All right.
And then down for it goes.
TV star.
Look at Marvin over there. You know what he's doing? He's looking for
I got
the part that says pen on it.
Hey, it's got a little bit of the pen label. You betcha, boy. That's why we buy pen balls. Now, mine says here, hey, if any pen ball should fail before the label wears off, send it in and look
We're at 322.
They think we are some racquetball players.
All right, let's see if we can do that. You know,
All right.
chemistry faculty, high school faculty, college faculty, we're usually on 3/4 pay. In other words, we work the 9 months and we have the summers free to do other things. John Showalter occasionally hires out as a summer carpenter. Here we go.
You see it? Put it in that box. Well, it's not stable.
And oh, that's
You're not really surprised at that, are you? Because of what happened to the ball, right? Look at that hard part.
We call it banana split.
Now we'll go through the table. I can't hit the same place twice. That's why they call me lightning. What do you think? Think I got it in there pretty good?
Is he driving through?
I didn't drive it all the way through.
All right.
My banana kind of gave up on me here. Is it in there nice and tight, Mike?
Pretty good. Have one of them check.
It was really strong. Not due to you. Turn around and show me how. I put it in there with the banana. Get it out of there. Don't hurt your hand. There you go. That's in there with a banana. Oh, thank you very much. And how could you do that? Because it was such a large temperature change. Did we tell you what the temperature of the boiling liquid nitrogen?
Anyone know what the temperature of boiling liquid nitrogen is? Oh, yeah, I know it's cold, just the temperature. No, it's not room temperature. Is it colder than Wisconsin in the middle of February?
Yes.
All right, in the news recently, we saw 77K relative to superconductivity, didn't we? 77K, that's the boiling temperature of liquid nitrogen on the Kelvin scale. On the centigrade or Celsius scale, liquid nitrogen boils at minus 196. Now maybe you're more familiar with the Fahrenheit scale. It boils at minus 321.
Now watch, the banana is not edible once it warms back up, is it? Because what happens is it breaks the cellular composition in there. Right? Because as the water freezes, it expands, bursts the cells. You get a freezer burn, like you talked about.
All right, what's in that balloon?
Hot air.
My wife says it's passion bread. What am I doing to it?
Cooling it down with that refrigerant, liquid nitrogen.
You look at changing the color of the balloon. It was red. What is it now? It's got orange, isn't it? Word we use for the change in color with temperature? Thermochromic. That balloon is a thermochromic balloon. You never knew that, did you?
Is all the hot air still in there? It is. What has happened to it, though? Some of it has condensed the water, and so on, even if possibly the oxygen, because the oxygen has a little bit higher boiling point.
Yeah, making a crepe. Stop it here. I'm hungry. Like I was a banana for lunch and it's gone.
The way I like to think about it is that temperature means really something to do with the speed of the molecules. So as we have decreased the temperature, we slow the molecules down. We slow them down so much that they cannot hit the walls of the balloon nearly as often. Even some of them, as you say, came into a liquid. That's why the balloon is so very flat. What happens if we bring it out?
Find out.
Now think of it, and you picture in your mind the molecules. They're speeding up because of the increase in temperature.
Your brain.
They're hitting the balloon much more often. Will it be the exact same size as it was when it was originally blowing up? It should be exactly the same size because the temperature of the room has not changed. For your gas laws.
What does it say? Chemistry is a gas at the University of Wisconsin. It's same identical size.
Now Marvin is a physical chemist. And physical chemists don't like to do things that are too many variables changed at one time. Did we change the temperature here? Yes. Did we change the volume? Yes. Did we change the pressure? Yes, we did. We changed them all. The volume went way down. The temperature went way down. The pressure went way down. He says, wait a minute, too many variables changed at one time. Let's do, when you do a problem, usually you change maybe two variables. A dependent and independent variable.
What do you do?
You got a way to do that?
I think I do.
See, I feel kind of bad that we took away Dr. Lang's lunch, and I knew he was going to do that, so I picked up some hard-boiled eggs on the way in. We peeled them and had them wrapped in cellophane.
Remember, they are peeled. Now, the volume of this thing can't change, can it? No, it's solid. The balloon, the volume changed, the pressure changed, the temperature changed. What I want to do now is just change the pressure and the temperature, keeping the volume constant. The hard-boiled gooey egg. You see, if I put my hand over here, the pressure inside is atmospheric pressure. If I were to cool it off, I'd pull my hand in there. What I'm going to do is pull the egg in.
Push the egg in.
I could pull it in or I could push it in, but I'm not going to, what you sometimes people say, hey, that flask is doing what? It ain't sucking an egg. Vacuums do not suck. Atmospheric pressure is pushing on it, isn't it? As the pressure inside decreases. Aha! Uh-oh. Uh-oh. Oh! We've got it in. How are we going to get it out? Key question. You can walk it on top of his head, or you can hand it to him and have a check and find a better way. How do we get it in?
These are all good signs of things.
Yep.
You gotta heat it to get it out, don't you? Because we cool it to get it in. Now, again, tell me what happens when I heat a gas. All right, but what in your mind, what do you see? You see the molecules expanding? The little molecule now becomes a big molecule. No, not. What you see in your mind is the speed of the molecules. You see the molecule now moving faster. So if I can use my warm hands and heat it up inside, I will increase the collisions of the gas molecules with the egg inside. The outside is atmospheric pressure. So I should be able to push the egg out of there. I'm squeezing the flask. The flask is certainly not moving. The reason I'm doing that is to heat it up. Is it moving? Did you ever imagine what a chicken must go through? That's why they make eggs like this, you know. They made them like a cube. Oh, Lord.
You ever been in a hen house?
Anybody ever been on a farm in a hen house?
Is there quiet in there?
Never quiet.
Why don't you help us then?
This is what they're doing.
Oh! Oh! Let's help here. Let's all run together now. I think he's got a constipated flask.
Help me. Help me. Chemistry can be fun, can it? We have a good time. But remember, in the back of that having fun, we're learning the gas laws. You've learned that there is a direct proportion between temperature and pressure. As temperature decreases, what happens to pressure? It decreases. As temperature decreases, what happens to volume? It decreases. So direct proportion. Peas and vegetables on the table comes from those two direct proportions.
We need to get a couple of volunteers. We want to get you involved if we possibly can.
Oh, yeah. 3
Oh, I see the lady way in the back there. Okay.
Yeah.
Pick one.
I get to pick one? Okay.
Michael, you can pick one.
We should have a young man, you know.
All right.
There you go.
All right, here we go.
All right. Right over there. Oh, come around here to the front.
We need to have you protect your eyes.
Now, all to wear those things. Now, you ought to see, we should have brought our glasses, Michael. We have psychedelic glasses that you can wear. All right? Yeah.
There you go. We would like very much for you to pick one of these 3 classes. Could you grab it by the neck and put your hand behind your back? You wouldn't hold. Okay. Your choice. You take a choice. Okay, turn around, show the audience what you got in your hand.
Turn around here. This is Jean. What color is Jean's to begin with? Blue. Charisma. How would you describe charisma? Clear and colorless. And Linda? It's Lisa? Linda. And Linda says, I'm pink. All right. Now what we want is some chemical out of their body. We want something that's a little acidic. You know what we can use? No, not spit. Carbon dioxide, huh? Any carbon dioxide in there? Give me a little bit. Give me a little carbon dioxide. Start blowing in here. Blow some bubbles. Blow some bubbles. Blow some bubbles. Blow some bubbles. All right. It's hard to blow in giggles too, isn't it? All right, now to the whole audience. To the whole audience.
You can't spit in there. Come on. Go.
In here, I put a little bit of this water and a little bit of phenol red. An acid-base indicator that is red or pink. When it's a little basic, we made a little basic, and we'll see if now Linda can make this turn into the acid color of the indicator.
What you have in this one?
That one over there, Jeans, I had bromothionyl blue, another acid-base indicator. It's blue when it's a little basic. Let's see if we can make it turn the acid color there.
Keep going.
Now, charisma is the middle one. This is a special test. This is what we call the bad breath test. Now, remember how charisma was at the beginning? Clear and colorless. Now, if it stays clear and colorless, then that means that your breath is just kissing sweet. But if it gets a little cloudy, it might say something about your breath.
Keep going.
Look at Jeans, all that turn. All righty.
Go.
I think you put a little too much ammonia in this one, but we put just a little ammonia to get it basic. Holy little mackerel, she's going to pass out before it happens. Oh, is it changing?
Let's try. There it goes.
It's going to get red, and then now what color is it?
Kind of orangish.
Kind of an orange color. It's going to
There's
go
gonna
to
go.
yellow.
Yeah.
Great. Charisma stopped, and thank the Lord. Stop.
I tell you, her breath is kissing sweet. So what she did here is you took your CO2 into lime water, good old-fashioned lime water, and so she made calcium carbonate or limestone. That stuff doesn't dissolve in water, so it settles out. What's the word for settling out a solid? That's right, precipitate. It's right here in front of all your friends who participate.
Let's give these people a nice hand.
Now you saw that what they were doing is they were bubbling CO2 into water, and it didn't dissolve very much, did it? It took quite a while to be able to do that. Here's some ammonia gas. It's not dissolved in anything, it just replaced the air in here. Here's a little water. Let me show you the difference between CO2 and water. Let me show you the difference in solubility.
It works.
Oh, it's coming up there.
Help us.
It filled the entire class, didn't it? flats. But this particular indicator, that bromothymol blue that Gene had, he started out with the blue form and went yellow, didn't he? Do you notice if you mix the yellow and the blue, what color do you get? Green, right in between. Well, let's dope this out. That was pretty strongly basic, wasn't it? All that water replaced the ammonia that was in there. Oh. What do you got there?
Okay. Being a beach community, I thought it would be nice to do something related to home. Now, I've done a lot of sailboat racing, long distance ocean racing, and spent a lot of nights very cold out looking at the water trying to figure out why am I here rather than in a warm bed at home. And I noticed something. There are a lot of very small sea creatures that excrete different chemicals. And they do interesting things in the water. And if you look really carefully at the surf at night, you can see something neat. You turn off the lights, Brian.
How about an ah?
How about wow? Wow! 85 wow. Now, is that real hot? Charles, is that hot?
Room temperature.
Cold light. Chemistry that is emitting light. We call that chemiluminescence. If it's a living organism, what do they call it? Bioluminescence. How about if you bang on something and you get light coming off?
You ever do the wintergreen lifesavers in the closet? You never done that? Yeah. Tell your girlfriend, come in the closet with me, I want to show you some chemistry. Take a little lifesaver in there. No, you don't do your teeth though, it hurts to take a pair of pliers. What's that called, Marv?
What? Oh, that's triboluminescence.
Triboluminescence. There's about 6 or 7 at least different kinds of luminescence. Luminescence means, of course, that the chemical reaction occurred, and instead of giving off energy in the form of heat, it gives it off in the form of light that's in there.
What are the 4 things that you need to be aware of relative to an explosion?
What do we have to have an explosion? 4 things.
Define an explosion.
Real general terms. 1, fuel. Right? Something to fuel. 2, heat, I heard, or a spark or something like that. 3rd, oxygen. Okay? And 4th, a container. A closed system, right? So that when the reaction does happen, the pressure and temperature push causes it to blow up. I want to show you a little bit of an explosion.
The fuel today is methyl alcohol. Good old thing. Here it says wood alcohol, perhaps mineral spirits. That'll be our fuel. Spark. I'm going to use as a spark generator something called a Tesla coil. You turn the lights off for a moment real quick. Right behind you there. This is a metal can. It's the pen can. Maybe you can see that spark right there. See that spark? Okay, it's about 50,000 volts. Hey, wait a minute now. Look, I can't get that to spark much more than about an inch. You can imagine what a lightning bolt must have to be able to go from the clouds down to the ground. That must be millions of volts. I can only get this to jump about an inch. You can turn the lights back on. My container, big budget here, nothing more than a poly bottle.
All right, ready? Fuel?
Yep, that's the fuel's methyl alcohol.
Methyl alcohol. Mineral spirits.
Okay, put a little of that in there.
Oh, yeah. Isn't there?
Here's the container. There's air in here, isn't there? Okay. Here's the spark. Why isn't it going? Oh, you remember I had the spark jump, didn't I? The little can, so I need a conductor. Let me use these 2 files. I have pre-drilled holes here, so I can stick the files right in the hole. Okay. How far apart should the files be? About an inch. If I have more than an inch, it's going to not jump. If it's less than an inch, if it's actually touching, then there'll be no spark. All right. Here we go. I have it in precisely 2.54 centimeters. Is that an inch? All right, thank you. She liked that. Do it again. Okay. All right, hang on. Let me. What did I say? 2.54. You ready? Don't stick your fingers in. They may be. Here we go. No. Here we go. Look. Did I break it? more things that we needed? Fuel, oxygen, a container, and a spark. We got the spark, we got the container. Do you know what you folks are doing? You're already thinking. You're trying to solve problems. And that's another thing that a scientist and a chemist does. They try to solve problems. They guess at what the problem might be or how to solve it. What if we got a fancy word? A hypothesis. And I've heard you say maybe it's the fuel. Let me check. Let me see if there's some fuel in here.
There's fuel.
Sure is. I see lots of fuel.
Well, it must be the oxygen, huh?
All right.
Let's replace that. Yeah. What's he putting in there? Well,
Boy, you give me more credit than I'm worth. My lungs are not 150% efficient. In fact, they're not even 100% efficient.
yeah, let's hurry. We gotta get these people out of here. So you're trying to replace that oxygen. Your lungs are only about 15%. So you're putting oxygen as well as carbon dioxide in there. What do you think? Got enough oxygen back in there? Yeah.
2.54.
2.54 centimeters.
Here we go. Let's see if it was the oxygen, folks.
Whoa! Yep. It was the oxygen. You know the explanation of that process. Now we do a little bit bigger. This is not really like. Have you ever seen this? Have you seen this, Patrick? All right, lights off, please. Set her right on the middle there. Set her down. All right, okay, there. Another match in there, would it work? Why? It's out of oxygen. It's the same sort of thing. This one didn't last very long. I've had that last for a minute.
Wow. Dancing flame.
All right, last one, huh? What's a balloon? What's in this one? How do you know? It's lighter than air, isn't it? And indeed it is helium. These gases are not helium. We're going to ignite the gas inside. So we're going to take the candle and touch it to the balloon and see what happens.
Now, if this is indeed helium, should there be any loud sound? Well, what sound should you hear? Just the popping of the balloon as if I stuck a pin into it.
Let's do it. Listen, I don't like to hold my ears. Now you're going to pop it out.
Whoop, fire extinguisher.
Nothing. Inert gas. Right? All right, this one has twice the lifting power of helium.
Means it must have half the molecular weight.
Has half the weight. Hydrogen. Hindenburg, 1937.
Lakehurst, New Jersey, with the lights off, please.
Lights off, don't hold your ears. It's a beautiful sound, real low sound.
I feel like the Statue of Liberty. Now, the only reason we heard a sound was the balloon had to rupture first, the flame that ignited the hydrogen as it began to mix with the oxygen. This time we've got the oxygen already in there. Folks, it's going to be like a shotgun shell going off in here.
Now we can
You
take the
must
dust out of your
protect your ears. Please do not stick your fingers in your ears before the obvious comment. No, cup your ears. And we will not do it unless everyone, including the people running the cameras, cup
Please,
their ears.
please do it. We don't want you to hurt your ears. It will. You'll feel it on your chest anyway.
Back, please.
There we go.
I'd like to thank Dr. Showalter and Dr. Lang for coming. You are excused.